Hi students, Professor Nugent here. In this video, we're going to discuss asymptotic normality and how to make use of it. When we bring in the sixth multiple linear regression assumption, that is that the errors are normally distributed, that is so that we can make practical inference, so that our t statistics are distributed according to a student's t distribution, our f statistics are distributed according to an f distribution, and we have some critical values that help us make decisions about whether our estimated coefficients are statistically significant. However, economic data are often not normally distributed. Okay, a normally distributed random variable is symmetric about the mean. It can take any positive or negative value, and more than 95% of the observations are within 2 standard deviations above the mean, among other things. An example is a data set, data on 401k participation rates. You can see here that the data are, let's see, you can say that there's an interesting skew here, that most of the data are bunched around a 100% participation rate. And there are very few observations around 0. And so we do not see a symmetric distribution. There is definitely not a symmetric distribution here. And it doesn't look like this distribution can take any positive or negative value. So it would be hard to say, gee whiz, that this distribution is normally distributed. So what are we to do? Well, what we can do is we have a very useful tool called the central limit theorem that's going to help us conclude that OLS estimators satisfy asymptotic normality. Right, so we will rely on the central limit theorem so that they are approximately normally distributed in large enough samples. Okay, students, let's put these thoughts into a theorem. Using the 5 Gauss-Markov assumptions, including homoscedasticity, we can write that the square root of beta j hat minus beta j is asymptotically distributed normal with a mean of 0 and variance of sigma squared over aj squared, where sigma squared over aj squared, this is the asymptotic variance of this term. Okay, aj squared is the probability limit of n to the negative 1 of the sum from I equals 1 to n of rij squared hat, where this rij hat, these are the residuals from a regression of xi on all other variables. So when we have this result, then we can say that beta j hat is asymptotically normally distributed, right? Because what's going on here is that the difference between beta j hat and beta j has a mean of 0, and so they're converging in probability. Number 2, our estimate of the error variance, sigma squared hat, is a consistent estimator of the error variance. And number 3, for all j, these standardized values, these are like the z-scores, right? Beta j hat minus beta j over the standard deviation of beta j hat is asymptotically normally distributed. And this is the standard normal distribution with a mean of 0 and standard variance of 1, standard deviation of 1. And not only is that the case for the standard deviation, which is unobserved, but that is also the case for the standard error, which is observed. It is rather estimated. That is estimated. Okay, so the intuition here is that regardless of the population distribution, the OLS estimators, when standardized, like the z-score, right? The value of x minus x bar over the standard error. These things have approximately normal distributions thanks to the central limit theorem. All right, so these conclusions come from the central limit theorem. So let's put this theorem to use. Let's put this to use. What this theorem implies is that because our student's t-distribution with however many degrees of freedom approaches the normal distribution as the degrees of freedom gets very large, the standard normal, then we can write beta j hat minus beta j over standard error beta j hat is asymptotically distributed t n minus k minus 1. So we can treat this term as a t n minus k minus 1 random variable even when that assumption of normality in the errors does not hold. So this is super useful. So we have that we can treat this as a random variable, which is asymptotically distributed according to the student's t-distribution, even when our errors are not normally distributed. Super useful. Cool. The other thing that we saw that was great is that sigma squared hat is a consistent estimator of sigma squared. And this is what appears in the standard error for each beta j, that is the variance of beta j hat is equal to sigma squared hat all over SSTJ 1 minus r squared j. And as the sample size grows, then sigma squared hat is going to converge to sigma squared. That's what consistency means. The r squared j approaches some number between 0 and 1, and the total sum of squares for variable j, well, observe that the sample variance of x, j, that is just equal to SSTJ over n. So that SSTJ over n converges to the variance of x of j as sample size grows, and SST of j grows at approximately the same rate as the sample size. This implies that the variance is going to shrink towards 0 at a rate of 1 over n. All right, the variance is shrinking at a rate of 1 over n because SSTJ equals approximately n sigma squared. So if you have n down here in the denominator, then the variance of beta j is shrinking at a rate of 1 over n. Okay? So that is why it's so useful to have large sample sizes, because the variance gets smaller. Now we can also write standard error beta j hat as approximately equal to Cj over square root of n, where Cj is equal to sigma over sigma j times the square root of 1 minus rho squared j, where sigma is equal to the standard deviation of u, sigma j is equal to the standard deviation of xj, and rho j squared This is the population R squared from regressing xj on all of the other variables. And the last thing that I want to add is that all of these conclusions that we have made, they all extend to the F distribution equivalently. Thank you.